Greetings, everybody. So we are continuing our videos on chaos-based image encryption, and the topic of today is cropping, tampering, and noise attacks. So let me remind everybody, we are talking about symmetric encryption here. So we are using the same chaotic system to encrypt a signal, for example, an image, transmit it safely, and then at the receiver end, we are using the exact same signal, using the exact same, chaotic system, using the exact same initial conditions and parameter values to reverse the encryption process. And the classes of operations that we do is shuffling and substitution. Okay, shuffling means taking the pixels of the image and dispersing them throughout, like shuffling a deck of cards. And the second step, which is substitution, means taking each individual pixel and changing its value. Okay, so in the previous video that I'm going to put it in the description, we talked about the first process, the permutation process, or the shuffling, if you like. And we talked and analyzed about why it is not enough to guarantee full security for encryption, okay? It guarantees some sort of security, for example, to the naked eye, but against several statistical steps, it fails. And that's why we need substitution. Now we are done. We're gonna talk about the second argument here that, okay, if substitution is so good, then why do we need shuffling? I mean, because we're taking here each pixel value and replacing it with another one. So, the immediate thought is that this should be extremely secure, right? Well, the thing is that although substitution is very good as a process, we also need shuffling in specific situations to protect against some sort of attacks in the signal. So the most important attack is the cropping attack. Now think about it. Let's say we don't do permutation or shuffling at all, right? We only do substitution, for example, by exclusive OR. And during transmission of our encrypted signal, we lose some sort of information. Okay, here I have a black box, as you see right here, and let's say that this sort of information, this part of the ciphertext is lost, right? So, I mean, this doesn't stop us from decrypting the signal. What happens, though, is this. Um, Once we reverse the encryption process, the part of the cropped signal that was lost is gonna be lost again exactly as it is in the plain text file. Okay, so I lost this part of the encrypted image, and exactly this same part is lost in the original plain text, right? So we have a loss of information. The exact part that was cropped is the exact part that gets lost in the final plain text file, right? And the problem here is that, obviously, if this sort of part includes some important information, we completely lose it, right? And that's why shuffling, or if you like, permutation, is so important, because it can actually protect us from losing this sort of information in cropping attacks. By the way, this may be an attack, or it may just so happen through losses in the communication channel. So the idea behind shuffling is this sort of block right here that was gonna be lost during transmission, well, actually, if we perform shuffling first, we take all of these pixels that are inside this box and we disperse them throughout the image, right? So now all the pixels that were here in the original image are now shuffled and dispersed throughout the shuffled image. And of course, after we perform exclusive OR, the same holds, right? So in the encrypted image, if some part is lost, like this block right here, well, this block of lost information doesn't correspond to this block in the original plaintext, okay? Because this block right here actually includes some pixels that have been shuffled from the whole image. So this block right here may include some pixels from this area, some other pixels from this area, some other pixels from this area, some other pixels from this area, from all around. So in case I lose this part of the encrypted image, I don't actually lose a whole block. What I do lose, if this gets cropped out, I may lose some pixels around here, some other pixels around here, some pixels from here, here, and here. So all of this block is actually lost information from throughout the plaintext. And of course, this is a good thing, because if I lose a pixel here and here and here, it doesn't really matter. I can still make out what the image represents. So this is why shuffling is so important. And see the example, the result right here, right? This would have been the result if I didn't perform shuffling, right? Cropping right here, exact information lost right here. But since I perform shuffling, this part doesn't necessarily correspond to this part of the plain text. So what happens is this. When this part is lost, as you see right here, I have some noise, actually some lost pixels, but they are dispersed throughout the whole image, not just in this block right here, okay? So this means that I don't really lose this information, this block of information, because the information lost is dispersed throughout the plain text, okay? And that's great because this makes the image readable throughout. And of course, this also happens even if I lose even more information, right? So here I have a bigger part that's cropped, but again, the final image, of course, is very diluted, but still makes sense. And even if I lose half of the pixels, okay, so here half of the image is lost in the encrypted case, but still I can make out the shapes of the final image, right? And even with more loss of information, 75% of the image lost, again, of course, very diluted, very noisy result, but I still can make out that it is the Pepper's image, okay? So that's why shuffling is so important. And of course, apart from cropping attacks, we can also have other types of attacks that try to, change the shape or the information inside the plain text, the ciphertext, I'm sorry. For example, we have a tampered image here where I didn't actually crop the pixels. I didn't remove them, but I replaced them with some other information, as you see right here, another image. The result is exactly the same as before. I don't really lose that information in a specific uh, range. I lose it throughout the text, even if 50% of information is tampered, or even if 75% of information is tampered. So using only this part of the ciphertext, again, of course, very noisy result, but again, I can make out that I still have the paper's image that was originally encrypted. So this is why shuffling is extremely important. Okay. And one other thing I need to mention here has to do with noise resistance. Of course, different types of noises will have different results, but overall, if our encryption works correctly, we can be somewhat resistant to noise as well. But Gaussian noise is more difficult. With salt and pepper noise, things are much easier. So if the ciphertext is corrupted with a little bit of noise, like 5, 30%, even 50 or 75%, I can still make out the original image. Okay, of course, this has to do with considering both permutation and substitution operations. But you see right here that even if I have 70% of salt and pepper noise, of course, the final result is very noisy, but I can still make out the shapes in the original Pepper's image. Right. So overall, of course, this has to do, as I said, with both permutation and substitution. But for cropping and tampering attacks, as you can understand, shuffling is extremely important to make sure that all the information lost is not on a specific block, but it is actually dispersed throughout the text. So no, you cannot just do substitution. You also need to do permutation, right? So thank you very much, and I'll see you in the next video.